So we'll also I think so now we conclude like the section on like the different state of the art methods, and then we will look at a bit more on like these kind of emerging areas which are like underexplored, but then they're really promising future directions. So we will discuss two such areas. One is physics and the other one is like the event cameras. So like a physical based simulation of deformable objects is like a very well studied area in the last 2-3 decades. And then the simulators can actually very accurately model the deformations by imposing like the true physical laws. So they answer the question like how does an object deform given its material properties under some applied forces. So similarly, rendering also achieved with like a physically based simulation of light transport with ray tracing or path tracing. But however, when it comes to the problem of these are actually, both of these are like well posed and forward problems. However, when it comes to reconstruction, uh, when it comes to reconstruction, this is inverse and an ill-posed problem. And then most of the methods instead of truly modeling the physics of the reconstruction, they make like a geometric approximation of the physical behaviors, such as isometry, for example, or like skinning. And so we already discussed actually two works which impose physics. So one was this work by Uveli, which can model the non-rigid deformations of the skirt using physics simulation, and then they do it as by training using a physics simulator, and then it's a soft constraint because it's not seen during the test time. So there are also methods, for example, this work which uses the differentiable physics as a hard constraint, where the reconstructed outputs are really the output of the simulator. So apart from these, so in generally, in the last decade, there have been amazing progress in 3D vision, using learning-based methods. But in the past few 2-3 years, there have been also like an emerging trend of combining physics and learning. So one of these works by Shimada et al, a neural physcap, which actually does this motion capture, works in a sparse setting, and then they can do like a motion capture from single images. And then here, even though it's a neural approach, it can, for example, it can apply like environmental and physical constraints, such as it prevents food flow penetration and any unnatural body postures, because the output is run through a simulator. But extension of this motion capture to, for example, to get a human performance capture, it's really not trivial. And similarly, recently there have been a number of works, for example, Snug that Rishabh talked about, and neural cloth simulation, which can, for example, do garment animation by encoding the pose and then the garment dynamics in the neural network, but then it uses physics-based losses for supervision. So they can essentially do a physics-based simulation. So similar ideas, similar losses, could also be explored for the reconstruction problem. So generally, the future directions include there are for example, we need a full physics modeling of complex objects, not just simple objects. For example, even though human is non-rigid, the different body parts, for example, the skin, muscle, hair, and clothing, they all behave very differently, and they should be modeled together. And also there's need for really accounting for many physical phenomena, and not just elasticity, which is considered previously, for example, the contacts, collisions, plasticity, and fractures, etc. And recently there have been interesting progress in combining physics, with physics informed neural networks, which for example, could use physics as loss functions, and then they allow a fast, so having these neural networks aware of physics could really solve some of the computational issues, and achieve fast inference, and also bring memory efficiency. And another interesting direction is to use of differential physics simulation for the reconstruction task. So another emerging area is this event cameras. So event cameras are basically like these vision sensors, which like unlike RGB cameras, they do not capture the entire intensity frame, but they record per pixel change in the brightness. So they have the advantage that they have ultra high temporal resolution, so there's like really less or virtually no motion blur, and they also can do they get high dynamic range images. So one like some of I mean so in the past few years, like there have been some works, and one of the state of the art work is like for human performance capture is this event cap, which uh, which takes like a hybrid input of like these events and then the grayscale images to do the reconstruction. So it supports both like the parametric SMPL model and as well as the like a rigged and skinned human template. So another work, like they improve on this, like in this like they consider only the first frame of the they only take like a single frame of grayscale image and then use events for the rest of the frames, and then do like a motion capture for this, like they track the optical flow in the event stream and then they use a warping loss. There have been also works which of reconstruction with event cameras, which specifically focuses on hands, called event hands. So in here, like it's a data driven approach, and then like they train it with a synthetic data set, and here compared to the previous two works, they do not require any kind of RGB input or like a grayscale input, and they regress the parameters of the manner model. And then what they noticed is that, for example, that they noticed that like events which are like trained on the this method which is trained on like a synthetic data set, it generalizes well to the RGB sorry, generalizes well to the real data setting, because like this event, they demonstrate that these events are like more abstract signals when compared to RGB. And so because of this with the event cameras, like can um, they have high temporal resolution, so you can do like a high speed motion reconstruction and using much lower power or bandwidth, and then it also works in like low light settings as well.